In this example, we are going to see a counter analysis. So here it is a specific application of our FSM analysis. So the difference is that, as you can see, there is no input to the system. So therefore, you cannot classify this as a Mealy's or a Morse model. And also, the state variables are also the outputs. So here we have basically three outputs or three state variables. So as we can see that this is a counter, and so the counter actually counts through a sequence and without any input. So the input is technically the positive edge of the clock, makes it to actually go from one state to another. So the idea behind this is that we will first start with an initial state, which is by default 0, 0, 0, and then we will see what the equation leads to, the next state equation leads to, and so once we get the result, we then assume that as the current state and then substitute that into the next state equation to get the other state, and then repeat that until we go in a loop. So in this particular example, as you can see, since we don't have an input, so we need to actually try to evaluate these values, that is inputs to your D flip-flop. And so here, as you can see, we have Y0, and we have AND of pretty much Y1 and Y2. So therefore we have basically Y0 XOR Y1 and Y2. Similarly for D1, it's basically an XOR of Y1 and would be Y1 and Y2. So therefore that's what we have here. And similarly for the case of as you can see for D2, it's going to be Y2 bar. So it's simply fed there, so that's just simply Y2 bar. So now we have these equations. So now what we do is we assume that we have our initial value is 0, 0, 0. So we substitute in here. We also know that our next state value, which is D2 plus, so this actually indicates D2 plus, D1 plus, and D0 plus. And that is also going to be the same values, the values of, as you can see, Y2, Y1, and Y0 is also going to be your outputs. So anyhow, D2 plus is going to be nothing but, by substituting that, it's Y2 bar. D1 plus is nothing but Y1 XOR Y2, and D0 plus is going to be Y0 XOR Y1 Y2. So when we actually substitute this in zeros, so as you can see, this becomes 1, and this is Y1 XOR Y2, 0 XOR 0 will become 0, and then we have Y1 XOR Y1, this is also zeros, so therefore that result is also 0. So we get 1, 0, 0. So the next state becomes 1, 0, 0. Now we move this value in here, 1, 0, 0, and then we then compute what the value is. So therefore again, when we substitute this, you will get Y2, the D2 plus value is 0, D1 value is, as you can see, will become 1 XOR 0 will become 1, and then similarly the last value will give you 0. So it goes to this state, and then we move this state as our current state, and then we recalculate for this particular equation. So we compute that until we actually go onto a loop. So here's our loop. So for some instances, let's say if not all these states are possible, then we will need to substitute those unused states, and then we should also be able to do our state diagram. So how do we go about doing our state diagram? So in our state diagram, we will just assume that this is a state S0, S1, S2, S3, 4, 5, 6, and 7. So in our case, we don't have any inputs, so it's simply S1, S2, S3, S4, S5, S6, and S7, and without any inputs, it's actually going to go through these transitions and then come back. As you can see, once you have 0, 0, it's going to go back to that state. So this will be the state transition graph or the state diagram for this particular counter. So here is another example. Here in this example, as you can see, we are using a D flip-flop and a JK flip-flop. So we have again one input, which is X, and we have two state variables A and B. So whenever we are going to create a table, so it is going to actually have X, then AB, and then we are also going to have A plus, B plus, and then we are going to have Z. Now as you can see here, Z is made up of values AB and also is dependent on X. So therefore this is going to be a Mealy's model. So therefore here we will actually have instances when X is equal to 0 and X is equal to 1, and then similarly X is equal to 0 and X is equal to 1. So here we can actually have the state, which is going to be, as you can see, we compute the equation for Z, which is shown here, and then we also see that for this we have D plus or DA plus is given as simply as the value of DA, or in this case it's actually would be simply A plus is given as D of A, and D of A is given by D of A is A dot X, and A plus X, and dot B would be A plus. So therefore that's what is given here. And similarly for this our B plus equation, because it's a JK flip-flop, that will be J B B dash plus K B dash dot B. So therefore that's what we substitute here, which this is for your J of B with B dash, and then you have KB is nothing but X dash of dash will be X, and then you have B, and this is its expanded form. So once you have these values, we can then populate our long table. So the long table is shown here, and now we can see that we can also represent this as a compact table. So where we have this is our function A plus B plus, which is this is actually called our next state. This is your current state, and that's your output. So here is your 0, 0. So whenever we have X is equal to 0, we go to 0, 1. That's what it is. When we have 0, 0, when X is equal to 1, we also go to 0, 0. And here the output is 0, and here is also the output is 0. So that corresponds to that row. Similarly, we can populate this table as we are shown. We then use symbols to denote our state variables. So once we have the state variables, and as I said earlier, this is a Mealy's machine. So therefore, let's say from S0, we go to S1 or S0. So here you can see when it's 0, our output is 0. We go to S1. When the input is 1, output is also 0. We are staying at S0. Similarly, when we have S1 Here we're going to 0 0 when the input is 0, output is 1 this time, and then when we are having an input as 1, our output is 0, we go to S2. So that's basically S2. So similarly, you can populate this as we have shown, and so this becomes your next state table, and this is your state transition graph. So in summary, in this module, we have seen about two types of machines or sequential circuits, Moore's and Mealy's. Students are expected to understand the difference between Moore's and Mealy's machine, how you can identify Moore's and Mealy's machines from circuit diagrams, as well as state transition graph. And we have also seen many examples of FSM analysis. That is how you can actually get from the circuit diagram to the next state equation, or the next state table, or the next state graph or state transition graph. We also saw analysis of a counter circuit, and students are required to summarize the procedure to do the analysis of finite state machines. So first and foremost, you need to identify your inputs, you need to identify your state variables and your outputs. Then you determine the input equations for the flip-flop. So in other words, if you have a flip-flop, you need to determine the equations at that point. And once you have determined that, then depending on the type of flip-flop, you would use your next state equations of the flip-flop and then try to derive, say, x plus, which is the next state equation of the flip-flop with the circuitry. And next, you would actually try to derive the truth table by applying inputs to or values to your inputs and your state variables, whatever you might have, and then equate your next state equations based on the next state equations values for your next state variables. And if you have your output too, you have to determine the output equations too. All right, thank you.